Hey everyone! So today we're just going to be going over the practice problems that are provided in the course materials online. These are Solomon's practice problems from Chapter 1, and they're just from our course materials. So I'm just going to work through them and explain to you guys how I would work them. So for the first one, the greatest degree of ionic character. What that means, ionic character, is there's some different types of bonds, right? There's nonpolar bonds, and that's when, like, say this is some electron density. Two atoms are equally sharing the electron density. So there's not a pull to one side or the other, it's just nonpolar. If one of these is stronger, it's going to be an uneven pull, and one side will have more of the electron density than the other, and that will have a partially negative charge. If it is a ionic bond, it's considered that the electron density is fully pulled over to one side, and that side is negative. And the other side is positive, and they hang out near each other because one's negative and one positive, and that's where their bond comes in. Really, though, it's not like, oh, and now suddenly this is ionic. There's more of a scale of polar moving towards a more ionic bond. So that's what this is asking, is which of these is going to be like an ionic bond? So one way you can look at this is go online, find out the electronegativity for different atoms, subtract them from each other, and find out what the dipole moment would be. That's not really practical on an exam. That's not something I do regularly. So what you can do instead is look up and see which one of these are furthest apart on the periodic table. So what I mean by that, I don't have a periodic table handy. Shame on me as a chemist. I'll use a smug though. So fluorine is the most electronegative atom, right? And we learned in general chemistry that electronegativity increases as you go towards fluorine. So up and over, it increases. So usually the further apart on here, the more difference in electronegativity there's going to be and the stronger dipole moment. So I would assume that if we're looking at these pairs, we've got carbon, chlorine, and bromine. So hydrogen and carbon, they aren't too far apart. It looks far because there's a space in between, but that's not a terrible distance. It's close-ish. The hydrogen and the chlorine are pretty far apart, and the chlorine is really close to fluorine. So that's one of the most electronegative items. So that's probably going to be pretty far. Bromine is less electronegative than chlorine, so you can eliminate any of the ones with chlorine now that we know that, or any of the ones with bromine now that we know that chlorine is more. And bromine and chlorine are really close together. So we can, that mark right there is a mistake, a danger of writing in pen. So we can narrow it down to these three. Well, hydrogen and chlorine are further apart than either of the other two, so I'm going to narrow it down to B. And that's how I'd work through a problem like that. Alternatively, you can look it up, but that you're not going to have that option on an exam. So what would the Lewis structure be for CH3, CH2, O2H? Anytime I'm doing a Lewis structure, I start by looking at the valence electrons. So for carbon, there's 4, and we have 2 carbons, so that's 8. For hydrogen, we have 3, 4, 5, 6 hydrogens. They each have 1 valence electron. Oh, I flipped these. So this is electrons. This is number of atoms. This is number of atoms. This is the number of valence electrons it comes with. So 6 times 1 is 6. And then for oxygen, we have 2. There's 6 valence electrons on oxygen, and there's 2 oxygens present, so that's 12. So that adds up to 6 plus 8, 8 plus 8 is 16, 26 valence electrons. So the next thing you have to do is figure out the base, like backbone of this molecule. And the nice thing in organic chemistry is when you have this condensed formula, that gives you a clue as to what your structure is going to look like. I'm going to try to zoom in a little here. Yeah, that's going to give you a clue to what your structure looks like. So the carbon right here is going to have 3 hydrogens around it. And once you get to the next carbon, that is usually a sign that we're moving on. Now this carbon has 2 hydrogens in it. So you have a CH3 unit and then a CH2 unit. My handwriting is not very good, but I promise those are hydrogens. That's why we have a shorthand in organic chemistry, is because we have bad handwriting. And then you're going to have 2 oxygens that will be bound together, and then a hydrogen. So that's your base baseline or backbone of your organic molecule, and you know that from the CH3, CH2, two O's, and a hydrogen. That gives you a clue as to this structure. You can see the CH3, CH2, two oxygens, and a hydrogen. So let's count up the number of electrons we've used here. 2, 4, 6, 8, 10, 12, 14, 16, 18. So minus 18, that's going to leave us with 8 electrons. And the only ones right now that I'm seeing, the only atoms I'm seeing that are lacking a full octet are these oxygens. So I'm just going to fill those in. 2, 4, 6, 8. And now nothing should have a formal charge. Everything seems to have the proper number of valence electrons. So that's what I check for. Does everything have 8 valence electrons? Does everything have a neutral formal charge, if that's possible? If the answer to those questions are yes, that's probably a good indicator that that's the right structure. So the right answer choice is going to be whichever one looks like this. And I think that's answer choice A. Yeah, because this has a double bond here. And when you're going through problems like that, you can look and eliminate any that have, just to narrow down your answer choices, any that have too many valence electrons, like if there's 10 or 12 around one atom, or if there's a charge in the structure, even though there's not a charge when they gave you the structure, if that makes sense. So the right answer choice here is A. Next question, again, a Lewis structure question. So carbon has 4 valence electrons, and there's 2 of them. So that's 8. Hydrogen has 1 valence electron, and there's 4 of them. So that's 4. And then oxygen has 6 valence electrons, and there's 2. So that's 12. So that should add up to 12 plus 4 is 16. Plus 8 is 24. Okay. So, and again, now we need our backbone, right? So it gives us kind of the clue, CH3. And then this carbon dioxide structure is weird. You could interpret that as carbon with 2 oxygens, or you could interpret it as 2 oxygens off of this carbon and then a hydrogen. So just from knowing about organic chemistry, that usually this CO2H is a shorthand for C with 2 oxygens and a hydrogen off one of the oxygens. So that is how I recognize that. If you didn't recognize that, you would have to maybe go through like having this oxygen off to the side and having a hydrogen bound to the carbon and all these things. But I'm telling you now, if you can look out for this or this, those structures are going to look like this. Okay, that's the backbone. So you've got 2, 4, 6, 8, 10, 12, 14. So that leaves 10 valence electrons. So then I'm going to go through and fill all of our octets in. So this carbon only has 3 bonds, so it should get a lone pair. This oxygen needs 2, 2, 4, 6, 8, 10. So we've used up all of our electrons, but this one didn't get filled in. So what you can do is take these electrons and make a bond, and then instead it will look like this. And that is the right answer. It has all the valence electrons, and it has a neutral charge, so that we've got everything we're looking for. You can quickly eliminate wrong answers on here if they have too many carbons, too many oxygens, too many hydrogens, or if there's too many bonds to a carbon. Those are all options. For example, here, if you look at the formal charge, this oxygen comes with 6 minus 3 for the number of bonds and 2 for the number of electrons. So that leaves a +1 charge on both of these oxygens. So you can eliminate that answer choice. Same thing here. This hydrogen has 2 bonds to it. Hydrogen can only have 2 electrons, 2 valence electrons. That's a full octet for it. So for it to have 2 bonds, that's the equivalent of 4. So you can eliminate that right away. This structure looks like it has too many hydrogens. So 1, 2, 3, 4, 5, 6 hydrogens, but there are only 4 in the original. So you can go ahead and actually get rid of that one as well. So that basically only leaves you with these bottom 2. And this carbon does not have a full valence set. It has 2, 4, 6, and that's it. So you can get rid of this one. So even if you didn't know this structure, another way to approach the problem would just be to go through and get rid of anything based on what you knew about Lewis structures from your general chemistry class. And that would land you with the same answer. So that's how I would approach working that problem. If me calculating this formal charge was confusing to you, we're going to go over that in a few questions. And right now, I think these Lewis structure questions seem really involved, but when you're used to looking at organic molecules, as you will be as the semester goes on, you'll be able to see that and know right away what it looks like, and you'll be able to condense it change it from the condensed formula to the bond line formula pretty quickly. So that skill is going to build up. Okay. Oh, formal charge question. Here we go. So formal charge is the number of valence electrons, and you can find that by looking at a periodic table and the column that it's in, the number in the one section. So if it's 13, the 3, if it's 16, the 6, that's going to tell you the number of valence electrons. You should have learned that in general chemistry. But you take the number of valence electrons that the atom naturally has according to the periodic table. You subtract the number of bonds, and you subtract the number of electrons. Another way people think of that is valence minus lines minus dots. If that's easier for you to remember, because sometimes people get all crazy and say the number of electrons represented in a bond divided by 2 is kind of weird. These are the 2 I recommend using most often. As long as you know lines represent bonds and dots represent electrons, I'm fine with that. So if we're looking at the carbon, the formal charge on the carbon, we have 2 bonds. So -2. Oh, I wrote carbon. Carbon has 4 valence electrons. -2 bonds minus 2 electrons equals 0. So that formal charge on the carbon is neutral. If you wanted to calculate for chlorines on here, you could. It's weird they don't have any lone pairs around them, but chlorine comes with 7 based on the column it's in. Minus 1 bond. And we're assuming that there's lone pairs all around here. Normally they'd be on there. If there wasn't, the charge would be 7 minus 1, and that equal +6. But that's really unstable. So then we've got, if we have all the lone pairs around, you'd have 7 minus 1 minus 6 electrons equals 0. So they're neutral too. So that's just a trick if you feel like, okay, I know how to calculate the formal charge on carbon. This is easy. You can challenge yourself by then calculating the formal charge for everything that you see. And if you're not sure if you got the answer right, you can always email me or reach out, and I can respond with if that was the right answer or not. Okay, which structure contains an oxygen that bears a formal charge of +1? The tricky thing about these, you want to make sure you don't find one and stop because multiple answer choices are there. So we're looking at oxygen. Oxygen starts with 6 electrons, 6 valence electrons. So for 1, this oxygen has 6 valence electrons minus 1 bond minus 1, 2, 3, 4, 5, 6. 6 electrons equals -1. The other oxygen starts with 6 electrons minus 2 bonds minus 1, 2, 3, 4 electrons is 0. So both neither of those are right. There's just a -1 and a 0, so that's not the +1 we're looking for. For both of these oxygens, they have the same number of bonds and electrons, so both of them start with 6 electrons. Both of them have 1, 2 bonds, and then have 1, 2, 3, 4 electrons. So both of them have a formal charge of 0. And over time, you'll get used to seeing an oxygen like this, and you'll recognize much more quickly that the formal charge there is 0. You'll just get used to it. But a lot of times students will get mixed up because they're not sure if they count these bonds each as 1. You do. A double bond would count for 2 electrons. That's why some people, the number of lines is easier to see because there's 2 lines off of that. For structure 3, that's 2. We're looking for +1, so anything with 2 in it is not right. So you can go ahead and get rid of answer choice D, and you can get rid of answer choice A, and you can get rid of answer choice E, just by knowing how to calculate those formal charges. So we know 1 and 2 both will not be in the right answer. So answer choice 3, oxygen starts with 6 minus 1, 2, 3 bonds minus 2 electrons equals +1. So that's a keeper. And there's only one answer with structure 3 in it, and that's answer choice B. So that's probably a right answer, but just to be sure, I'm going to double check 4. So structure 4 has 6 valence electrons, 1, 2, 3 bonds, and 2 electrons, so that's also +1. There's a 1 there, it's positive, so that also is good. So answer choice B, I'm getting pretty confident. Just in case, let's check answer choice 5, or structure 5. So this oxygen has 2 lines and 2 lone pairs, just like we saw in answer choice, or in structure 2 and 1. So 6 minus 2 bonds minus 4 lone pairs is 0. And then this is similar to the structure we saw here. 6 minus 1 bond and 6 electrons is -1. So 5's not right. So answer choice B is correct. So if you're ever not sure, use what you already know to eliminate answer choices, and then you can narrow it down, and that will really help you. Okay, which molecule has a nonlinear shape? The one thing that bothers me about this question is they did not include lone pairs. So if you've seen these structures a lot, you kind of can figure them out. Or they are all presented as neutrals, so they all have as many lone pairs as they would need basically to make it a neutral molecule. So this CO2 actually looks like this. The water looks like this. The HCl looks like this. The, I think that's hydrogen cyanide maybe, looks like this. And then this is what the alkyne at the bottom looks like. Okay, so we've got all of our structures drawn here, and this is actually really a Vesper Theory question. So Vesper Theory, you may remember, or you may not, from back in Gen Chem. I think it's spelled like this, actually. So it's like Vesper. It's not really Vesper, but the way that you basically talk about Vesper Theory is the number of electron domains. So I'm going to grab a notebook and do a quick review on Vesper Theory. If you feel like you remember this really well, then you can skip ahead. But Vesper Theory, so if you have a molecule with 4 things around it, our instinct is kind of to draw like this. And you'd assume, okay, there's 90 degrees between it, right? But in real life, you have 90 degrees between these, and then if you can 3D imagine coming out of the page, if you can imagine this angle right here, if my pen is it, then right here, that's 180 degrees. So this angle coming out of the page is 180 degrees. So that's actually not ideal for these molecules because some of them have a lot of space around their electrons, and some of them have less. So they take this shape that they call tetrahedral, and it looks kind of like a pyramid. So if you can imagine this as a pyramid, and this in the plane of the page, and all of the bond angles here are 109.5. Another way to think about this or to visualize this is to have a modeling kit. So I highly recommend these for organic chemistry, but if our molecule looked like this, and they were all 90 degrees from each other, these would be really close together, and these would have a lot of distance. So the real shape that they end up taking looks like this, and all those are 109.5 degrees from each other. That's the angle between these, is 109.5. So Vesper theory is really based on this idea of electron domains, and the way that however the molecule can get as much space around its atoms that's what it's going to do. So for this question, it's asking which one of them are linear, or which one of them has a molecular shape that looks like this. And you'll need to know Vesper theory pretty well in order to answer this question. So the structure first for carbon dioxide. So this carbon only has 2 electron domains, is what it's called, or things attached to it. So its best bond line, or its best shape, is going to give 180 degrees between these 2 things. If you have 2 things coming off of it like that, it's usually going to be linear. So this is not our right answer because we're looking for nonlinear. For HCl, there's only 2 things. The best way to get from point A to point B is a straight line. There's no other way you could bond between these 2. There's not a central atom, so it has to be a straight line. So if it's only 2 things, boom, straight line. Here, this carbon-nitrogen bond, this is a little confusing, so I want to make this structure for you. So you can see how carbons bond together. So this is a carbon. Carbon has 4 electron domains, or 4 things attached to it naturally. It needs 4 bonds. If it's going to bond to something else and there's only 2 things between it, this will be a straight line. If a double bond is formed, there will be a straight line here, but this carbon by itself is Sp2 hybridized, or it's 120 degrees between. If there's 3 bonds, did you see what just happened? We went from 120 degrees. All these things this is bent from here to here. You can kind of see the bend. When this bond forms, now this is a straight line. So a carbon-carbon triple bond, or a carbon-nitrogen triple bond, will actually be a straight line. So both of these are 180 degrees. The carbon only has 2 things off of it. It's 180 degrees. So all that's left is the water. And probably a lot of you honestly have memorized this just from over the time, but oxygen has 4 electron domains as well in this case. It has 4 things around it. So it looks like this. However, only 2 of those electron domains actually have something on the other end. These 2 are invisible. So if you couldn't see these structures, it would just look like a bent molecule. So this is not linear, this is bent. And that's how we get to answer choice B. Okay, question 8. This is the first time we see condensed formula turn to bondline formula. So each one of these joints here is a carbon. I love bondline formula because I don't have to draw out all those hydrogens. For some reason, my hydrogens always end up looking like 4s. I will never understand it. So each joint is a carbon, and you just assume that all the hydrogens are there. So the way that this would be converted into condensed, or like a Lewis structure, would be 3 hydrogens around it, 2 hydrogens, 2 hydrogens, 3 hydrogens. So what started as a line that looked like this, 1, 2, 3, 4, 5 carbons, these represent the same thing. This is your bond line formula. This should be your Lewis structure formula. But drawing all those hydrogens is a lot harder than just drawing this line. So we just assume that there are implied hydrogens. Now this structure, structure 1, there's 3 hydrogens here, 3 here, 3 here, 1 here, 1 here, 2 hydrogens here, 3 hydrogens here. I'm going kind of quick. This video is already 25 minutes and we're barely not halfway through it all. So that's why I'm going kind of fast. But make sure you know where all those implied hydrogens are. The next thing you have to know, this is testing 2 things. Do you know what these structures mean? Number 1. And number 2, what is a constitutional isomer? So you'll learn that there's 2 different types of isomers. All isomers have the same number of atoms. So it have the same number of carbons, same number of hydrogens, same number of oxygens, all that. They have to be the same for both structures for it to be an isomer. But there's kind of 2 different types of isomers. There's the types of isomers that, say if you have 1, 2, 3, 4 carbons, and then you rearrange it to look like this. Both of those have 4 carbons. They both, I think they have 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so they both have 4 carbons, 10 hydrogens. That's the same. Or there's a different kind of isomer where this is called the constitutional isomer or structural, where it's just basically structured differently. They're built differently. Their construction is different. Or you have what's called stereoisomers. And that's the same thing. You'll learn more about it. They have the same number of carbons and hydrogens, so it's the same thing in that way. But what's different is their connectivity is the same. The way they're structured is the same, but they're arranged differently in space. So one of them might have a 3D structure that's different than the others. We don't talk a ton about these until I think chapter 4, and then it becomes a big theme. But for right now, you need to be sure you know how to find constitutional isomers. So then literally what I do for this is I count up the number of carbons, hydrogens in each of them. So 1, 2, 3, 4, 5, 6, 7 carbons. 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 Okay, 7 carbons in all of them, hydrogens. That's all there are carbons and hydrogens, so you don't have to worry about anything else. There's 3 hydrogens on a terminal because you need 4 bonds around a carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens is what I counted. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 as well. If, you're new to this and you're worried about missing one, you can draw a little hydrogen in each place that there's supposed to be one. That is a recommendation I have. Sometimes students will just draw lines like this, and I don't recommend doing that because what that means in organic chemistry, that looks like another line and it looks like a carbon. So don't do that, but you can and should draw in all the hydrogens if you're not sure. And so let's go to structure 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. Structure 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's only 14 hydrogens. And I've numbered all of them, so there's nowhere else another hydrogen could be that we missed. So all of these, C7H16, should be isomers, and this is not an isomer, it's just a different molecule. So the right answer is answer choice C. Okay, here we go. This is what stereoisomers look like. They are arranged differently in space. So these wedges and dashes represent spatial arrangements. I don't think we need to talk about that right now. It'll come up a lot later on. Okay, so they're asking which of these is an acceptable bond line formula for C4, C3, CHCl, CHCH2. So it's giving you a hint on what the Lewis structure is, but that's where I would start. CH3, CH, this Cl is a little ambiguous, but if a halide, like a fluorine, chlorine, or bromine, comes after a hydrogen, they act like hydrogens because they really only need one bond. So usually you can assume that's taking the place of a hydrogen. And then we have a C with one H and a CH2. So sorry, I shouldn't have drawn that right there. So it looks like this. So what jumps out to me right away, and I hope it jumps out to you too, is these two carbons don't have 4 bonds around them. They're short on their valence electron. So there's likely a double bond there, and then everyone's satisfied. So that's what we're looking for. I'm going to go ahead and convert this to bond line formula. So 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. There's a double bond right here, and one of them has a chlorine off of them. So this is the right structure. If you wanted to draw it like this, where your first carbon is up top, 1, 2, 3, 4 carbons, and your chlorine's off to the side, that's also correct. Both of those are correct. And that's basically what they do here. This is kind of a tricky question, is they basically want you to know, are all these the same? And I feel like that's kind of an advanced topic, but if you can see that each one of them has 1, 2, 3, 4 carbons, and the wedges and the dashes are just a way to represent where they are in space. All those have 4 carbons. All of them have, well, I numbered it backwards, but have a chlorine bonded to this carbon right here, just like we do here. And all of them have a double bond on this side. Then that indicates that these are all the same molecules. These are all valid structures. So answer choice E is correct. It's kind of a weird question. It's just kind of to get you used to seeing that 3D structure, to see the tetrahedral shape in action in organic chemistry. Okay, so next is resonance. Resonance can be hard. Remember, the rules of resonance are electrons move, atoms don't move. And that can be tricky when we're doing our bond line formula with the implied hydrogens, because sometimes we don't recognize that an atom was moved. The other thing is electrons will move, but anytime a bond breaks or a bond is formed, another one has to break or form to maintain the valence. So those are the big things about resonance. And I always start, this isn't a rule, but a suggestion, start with where the extra electrons are. So we call that the high electron density. Like the amount of electrons in the area is more, let's start there. So here for question 10, the high electron density area is right there where that lone pair is. And I also wanted to give you a kind of I think this is a review, or maybe you guys haven't talked about this before, but about how electrons and arrows move. So in organic chemistry, actually, I'll do it like this. If you have electrons and you want to denote them moving from one space to the other, you draw it like that. So if I had molecule A and the electrons went from molecule A to molecule B, you'd have an arrow with 2 barbs. And what that denotes is this movement of electrons. So this arrow indicates that this lone pair moved over here. If you have a bond between A and B, we'll make it a double bond, and the bond breaks, we'd say the 2 electrons that make up this bond are moving over here to electron B, that's how we would, or to atom B, that's how we would denote it. So your new structure would look like this. If we have a double bond and we get what's called a heterolytic cleavage, or it's making a radical, we've talked about radicals in Gen Chem, instead of doing 2 heads on the arrow, it just has 1. So that means 1 electron, actually I drew that, should be from the top bond. 1 electron from this bond is going to go to each atom. So then we end up with A, B, each with a radical. So that's why we draw all these crazy arrows in organic chemistry. So I'm going to show the resonance and the flow of electrons using these arrows. And I'm going to try to go slow so you can see why I'm doing what I'm doing. So this is kind of testing both of those for you. So if we start with this structure, and we have extra lone pairs here, that's where I'm going to start from. There's only 3 places that this lone pair could create a bond. And that would be on this line, or this line. It has to move adjacent. The lone pair has to create a bond adjacent. So if the lone pair tried to go here, that would make this structure. And the problem with this structure is you already had 3 hydrogens here. So if the bond goes here, then you have 5 bonds to carbon, and that's not possible. So that's not going to be a structure that forms. So that is not happening. If the hydrogen was removed, maybe that would work, but that wouldn't be resonance anymore. So the next place, I'm just going to draw our starting structure again. The next place that structure could go would be here. Now, one of our rules is maintain the valence. So a new bond was formed to this carbon right here. So we can break a bond to move to an electron, a lone pair. Here, if we broke a bond, a hydrogen would leave. That's not going to happen here. It will form a lone pair on the sulfur. So this double bond over here is unmessed with, but we formed a new bond right here. And to maintain the valence, we broke the double bond here, and it became a lone pair on this sulfur. So that's allowed because we didn't lose or gain any atoms the way we would have if a hydrogen broke here. We just broke a double bond and moved some electrons around. So that would create a negative charge. Boom. That's one of our right answers. Now let's see if we can go the other way. So if you start with our main structure here, our lone pair could go to this side. But again, we'd have to break a bond. And in this case, one of this double bond can break and go to the carbon. And you're not losing any atoms. You're just breaking a double bond. So only electrons are moving. So the new structure would be a valid valence structure. So we formed a double bond right here between these two. And then the double bond broke. We still have our 2 hydrogens. There's just a lone pair also in the carbon. It doesn't exceed a valence, so it doesn't break any rules. So this is also a proper structure. This one, hopefully you can look at it right away and recognize that hydrogen was added, and that doesn't work. That's not valence, that's just a new molecule. Or that's not resonance, that's just a new molecule. So the right answer choice should be B, 2, and 3. Okay. So then for question 11, this is a really similar question. So we have 3 options of where our excess of electrons can go. It can go here and a bond would break. It could go, I'll use different colors so that it's easier to follow. It could go here and this bond would break. Or it could go here and this bond would break. So each one of those, you can maintain the valence and you can break a bond to do so without adding any atoms. So I'm going to draw those out for you. So let's start with the blue one. If our structure, the lone pair moves here, this bond will break. There's only 2 hydrogens here, so adding a lone pair, that's fine, no problem. We have the right valence still. So this one's unmessed with. This one down here also unmessed with. Here we've taken the lone pair, formed a double bond, broken this bond for a lone pair. There's only 2 hydrogens that were implied there, so that's a negative charge. That's where your formal charge comes in. Your carbon starts with 4 valence electrons, minus your 3 bonds, minus 2 electrons, formal charge of -1. So that's how we end up with this structure. I don't know why they did the mirror image of it. It's kind of weird, but this and this are the same. If you just flip it around, you can kind of see that. I don't know why they do that. Just to throw you off. Hate that. Okay, next for the green one, if our electrons go here in between these 2, this bond can break and form a lone pair. So I'm going to draw that for you. This one didn't get messed with this time. This one's still there. This is intact. But we did form a new bond right here, and the bond that used to be here broke and formed a lone pair. There's only 1 hydrogen implied right here because there's 3 bonds. So into carbon. So here you'd still only have 1 hydrogen, 2 lone pairs, 2 bonds to other carbons. Your formal charge is negative, and that's how you end up with this structure right here. And then for the last one, our lone pair can go right here. So how do we get that structure? What happens next? And if you want to make these videos more effective, if you feel like you know what you're doing, you can pause these, try to get the right answer and see on your own, and just see how you do, and then come back and watch me solve them. So if this lone pair moves here, a bond needs to break to keep the valence. So it will to the end. There's only 2 implied hydrogens here, so having a lone pair there fills our valence. So we formed a bond right here, broke the bond that was here, and now there's a negative charge on that carbon. And that is the same structure as here. There's no way for these lone pairs to jump all the way over here and keep the valence, which is what they're talking about in this structure. Or even they're talking about that double bond breaking and forming a lone pair right there somehow. But there's no way to do that and get rid of this negative charge right here. So that is not a possible structure. So your only possible structures are 1, 3, and 4. So the right answer is, I would have gotten that wrong if it was to test. It's asking which is not a resonance structure. So number 2 is not a resonance structure. So the right answer is answer choice B. Okay. I know that's a little confusing. If you need more resonance practice problems, I recommend getting a book like this one. Preparing for your ACS exam, they have really good practice problems. Or a book like this one, Organic Chemistry as a Second Language. It's actually pretty useful. They have one for first and second semester organic chemistry. Okay. Now, which of the following species contributes more to the overall hybrid? We talked about this in class. The structure that contributes most to the overall hybrid is if it's neutral, if the molecule is neutral. So this molecule is not neutral. If it could be somehow, that would be the most stable formal charge, or the most stable resonance hybrid. It's not. So the next best option is the negative charge on the most electronegative atom, or the positive charge is on the least electronegative atom, or electropositive atom. You can look those up, or you can know fluorine, oxygen, nitrogen are some of the most electronegative. My teacher taught me FUN, F-O-N, so it's not really fun because fun's with a U, but that helped me remember. They're the same ones involved in hydrogen bonding. Or you can always bust out your periodic table and look for the most electronegative atom, and the ones closer to that would be more electronegative. So in this case, nitrogen is closer to fluorine than carbon. So nitrogen will be happiest with the lone pair. So you can go ahead and assume that any of these that don't have nitrogen with the lone pair are not going to be the most stable formal charge. Now the question is, are both of these valid resonance structures? And if you feel better, you can try to draw all the resonance structures for this if you want. I think maybe 1 and 2 are both valid resonance structures. The lone pair could move here or here. Either of those are valid, so I guess actually 2's not. This is valid, but it's not, doesn't have the negative charge on the nitrogen, so that's not a good option. This is not a valid lone pair because there's no way for this double bond to get over here. If this lone pair moved down here, there's 1, 2, 3, 4, 5 bonds to carbon with the implied hydrogen, so that one's not right either. So we've got option 3 or 4 are the only ones with the negative charge on the most electronegative atom. So are both of these structures valid? That's the question. Well, there's only 2 places for electrons to go. If this electron then forms a double bond here, this becomes a lone pair because you have to keep the valence. So that gives us structure 1. If the lone pair here forms a bond, then this one would break and form a lone pair on the nitrogen, and that gives us structure 3. So then the question is there a way that you could get structure 4? And I don't think you could, because it just looks like structure 3 with an additional double bond. And that adds 2 electrons to our structure that weren't there before, so that's a different molecule. So answer 4 is not right, and the only possible answer choice is answer choice 3. But if you only knew that the most electronegative atom should have the negative charge, and you knew that nitrogen was right next to fluorine, so it's negative, you could narrow it down to 3 or 4. And you could probably recognize that there's more extra electrons here than there are here. We only have 2, 4, 6 extra electrons. Over here we have 2, 4, 6, 8 in those double bonds and lone pairs. So that's a difference that you can look for. Okay, similarly, which of the structures is not going to contribute to the CO2 resonance hybrid? So this is tough because you've got to know the CO2 Lewis structure. I have it handy off the top of my brain, but you can go through the steps I showed you before where you calculate the valence out, you put the lone pairs around it. But this is a very stable structure. All of our valence are filled. The formal charge is neutral. So that's a good structure. So what resonance structures do we have? Well, no atoms can move, only electrons. There's a higher electron density here, so I would break a bond and form an extra lone pair, and you'd end up with that is not as stable as a neutral structure. So this is already going to contribute less than this. You could do the same thing on the other side, and it would also contribute less. So this is the most stable. So we're looking for not expected. This is expected to contribute a lot. Next in line to that would be these double bonds. I think these would be logical resonance structures that would contribute a lot. They won't contribute as much as this one, but they will contribute some. But this here with 2 charges and 2 negatives is kind of crazy. I have never seen a structure where you could have a neutral and instead you had 2 negatives and 2 positives. So I'm going to say this won't contribute as much. This structure is interesting, but because there's less charges, only a plus and a minus, I think it would still contribute more than this. I don't think it would contribute a lot, but I don't know 100%. Positive charge on an oxygen is not as good as a positive charge on a carbon. So if I had to rank these, I would say this contributes the most, and then these 2, and then this in the 3rd place, and this not at all. So that's why I would go with answer choice D. kind of a hard question because you really have to know a lot about what the Lewis structure looks like, how the electrons are going to move, and then which structure is the most stable. It's a lot to know all at once. Okay, Cis Trans Isomerism is if you have the same thing or the biggest groups on the opposite side and the smaller groups on the opposite side. That's called trans. And if they're on the same side, that's called cis. So in organic chemistry, that's most often you see carbon groups on the same side or the opposite side, and then you have an implied hydrogen here and here, implied hydrogens here and here. So this would be cis and this would be trans. So you have to have two different groups on each side of your carbons. So see, you have to have a CH3 and a carbon. You have to have an A group and a B group for them to be on the same side. And they have to be different. So here we have our CH2 CBr2. What that gives you is an H, Br, Br. Doesn't matter if you detach these and flip them around, you can't get different isomers. So that's not right. Oh, and also this is an example of a stereoisomer. It's different than a constitutional isomer because they can be built the same way, but it's just about how they're arranged. The condensed formula will be the same, but they're arranged differently. So cis trans isomers are a type of isomers. They're called stereoisomers. And then here for CH2, CHBr, what you get is only one Br. So again, cis trans isomerism is not possible because we don't have the same group opposite to each other or the same to each other. We have different groups there. For this one, for answer choice C, I'm just going to go all up in 15's room. We have a Br and an H, a Br and an H. So this so far is the only right answer that I see because this has the big bulky groups on the same side and this is opposite. So if you can flip one side around and get a different structure, then that's an isomer. So this has cis trans isomer. If you flipped this one around, you can't tell that I've done anything different. Those Br are straight up places, but it looks the same. So that's not isomerism. And then D, same thing. It has 3 bromines, so you can't tell if anything changes. If this swaps, the other side is the same, so it doesn't matter. And then this is all bromine, so that's the same as basically having all hydrogen. So the only right answer is answer C. Okay, 15. This is where we get into Sp2 Sp3 hybridization. So a quick and easy way to, well, let's talk about the theory behind hybridization. So you remember orbitals, hopefully. So orbitals are, you'll have your s orbital with 1, and your, let's do a different color to make this more interesting. P orbital. P orbitals have, there's 3 p orbitals and 1 s orbital. That's kind of hard to see, so I'm going to go a little bit. There you go. Okay, so say you have a carbon atom with 4 valence electrons, and they're all trying to form bonds. Well, you could have 1 in the s and 3 in the p. But the energy level for the s orbital is lower than the p orbital. So you'd have 1 low energy bond and 3 high energy bonds. That's kind of weird. So what happens instead is the blue and red mix together to make purple, and you could have 4 sp3 orbitals. But what if you're only trying to make 3 bonds? Then you would take only 2 of your orbitals from the p and 1 of your orbitals from the s. So you'd get 3 sp2 hybridized orbitals. So this is 3, that's 2. And you'd still have 1 of your p orbitals left over. And that p orbital can partake in pi bonding. or a double bond. So these are your sigma or single bonds. These are going to be part of your double bonds. So now let's talk about carbon. You have 4 bonds here. So this carbon has its 4 valence electrons, and instead of having 1 s orbital and 3 p orbital electrons, because that would be weird, they hybridize, and all of these bonds are made up of an sp3 orbital on the carbon side. Only an s orbital on the hydrogen side, because hydrogen only has 2 electrons, so only an s orbital. If there was a double bond, this right here, one of these would be made up of an sp2 orbital, and this pi bond would be the remaining p orbital. That's kind of complicated. If you want a faster way, what I do is count up how many things there are, and that's how many orbitals we need. So if we have 1, 2, 3, 4 things bonded, then we need an s, p1, p2, p3, sp3. If there's 3 things bonded, you need an s, p1, p2, sp2. The tricky thing with that is a double bond here counts as 1 because the second bond is not going to be made up of your hybrid orbital. So you have to know that if you're going to do this method. It's different than like when you're calculating valence electrons. If you have 2 things bonded to it, then it's an sp. So that's how I calculate quickly, but it's not the most proper way. Okay, so the question here, 15, is which for the C4, C5 carbon-carbon bond, what is the hybrid overlap? So it's asking what's the hybridization for C4, what's the hybridization for C5? That's all it's asking. C4 has 2 implied hydrogens, so there's 1, 2, 3, 4 things attached to it. So 1s, 3 p's is 4, so it's sp3. Carbon 5 has 1, 2, an implied hydrogen, 3, so that's sp2, because 2 p's and 1 s is 3 things bonded to it. This one's tricky because there's an sp2, sp3, and an sp3, sp2. Both of these would be right depending on which order you're putting it in, but it specifically asked for the C4 first, so that's why this should be your right answer. Okay, for question 16, this is just asking what the shortest bond is. And this is an old Gen Chem one. I remember me and I worked for a professor, and she's like, the more bonds you have, the closer you get together. So imagine 2 people, and she made us do this, standing next to each other, and they're holding hands. They can still be pretty far apart if their arms are completely unstretched holding hands, pretty far apart. But then if they hold their other hand, they're getting closer together. And if they're holding hands and their feet are touching, they have to be even closer together. So my hands, when it was just 1 connection, could be pretty far away, but with 3 connections are closer together. This is as far as I can stretch out my hands. Single bond, it's further. Triple bond, less far. So that is basically your answer. If you've got a triple carbon bond, that's the shortest one. That's just a review of Gen Chem. Which of the 3 following contains an sp2 hybridized carbon? So sp2 is going to have 3 main things off of it. So CH4 has 4 things, so that's sp3. Lone pairs count as a thing coming off of it, so that's sp3. These are CH3, CH3, but they're bonded to each other. So they each have 4, so both of these are sp3. Now, the absence of electrons, like forms in a carbocation, that's saying that it's missing electrons. So that is actually Sp2 hybridized. And this is Sp hybridized because each of these carbons only has one thing coming off of it. So if it's off of each side, so 2 things coming off of it, 1s, 1p, Sp hybridized. Okay, so the right answer for that is answer choice D. What's the approximate hybridization state of the oxygen in ethanol? So this is tricky. They don't give you a condensed formula, so you have to know that ethanol is this structure. But if it's an alcohol group, the carbon is going to be bonded to the oxygen like this. So this is the structure of ethanol. And it's got 1, 2, 3, 4 things bonded off of it. So that's Sp3 hybridized. And then the last one, what molecule is a central atom Sp3 hybridized? Well, we already know that it is for carbon. There's 4 things bonded off of that, so that's right. But there's in all of these, so we need to double check on all of them. If you remember the Lewis structure for ammonium, is it ammonia or ammonium? I can never remember. But for NH3, it has a lone pair, so that's 4 things. So that's Sp3 hybridized and H2O. So 4 things, so also Sp3 hybridized, so the answer is all of these. So that's kind of a long video. We went over a lot of review from Gen Chem, but hopefully that was helpful to you guys. And if you have any questions for me or if you need anything, please feel free to reach out.